Hi all, and welcome to the third and final part of this tutorial series to automate the game Asteroids. So today we'll actually be feeding in game data into our neural network so that we can rotate this ship. I'm doing this manually, of course, so that we can rotate the ship and shoot at the closest asteroid. Okay, so head into our code. I'll just turn automation back on. Okay, and head to our neural network file. The first thing I'd like to do today is to set up some error logging in our neural network class. The reason for this is that I'd like to be able to keep track of how well our training function is doing as we're training it. So let's set up a flag up here, just a constant. Let's call it log on, set it to true, and that's just whether or not to show error logging. And we'll need to keep track of how often we show this message. Like show a message. We don't want to show it every iteration because we could, in theory, be calling this train function like hundreds of thousands of times, if not millions of times. So let's set a log frequency. Initially we'll set it to 1,000, say. And that's just how often to show error logging. Error logs. And that's in iterations. In iterations. Okay, we'll have to set up a private member variable here, just down here. So error logging, this underscore, we'll keep track of how many calls we've had or how many iterations, so we'll call it log count, and it'll start the day at log frequency. And we'll also, because it's private, we'll want to set up some getters and setters. It's not technically private, I'm kind of making it private, I should say. So get log count, return this log count, set log count, this log count equals count. Head down to our train function. Now, what's the most appropriate thing to output here? I'm thinking the output errors, because the output errors are simply the target minus the output. So if the target's 1 and the output's 0.7, then the error is 0.7. It's easy to understand. So let's do our error logging here. Error logging. If log on, and if this.log count, if this.log count equals the log frequency, well, let's do a console output. So console log output errors. Now, it's a matrix, so we'll need to grab its data array. And there's only going to be one error because we've only got one piece of output. So we'll just do the first the first row, first cell. Okay. Probably prefix that with something so we know that what we're outputting, error equals that. Then we'll have to decrement the log count, so this.log count minus minus, because we don't want it occurring every iteration. And when that reaches 0, if this.log count equals 0, what will we do? Well, we'll just reset it. This.log count equals log frequency. Let's test that out. So currently we'll just need to turn our console on, reset it. Okay, here we go. So we got errors of 0.32, 0.29, 0.08, blah, blah, blah. It's going down slowly, isn't it? So this is our XOR gate logic that we used last time. How about we increase the number of samples? So go back to our other file, our HTML file. We'll increase the number of samples to, say, 100,000. And we'll increase the number of hidden nodes to 10. But because we're doing 100,000 samples now, how about we change our log frequency to, say, 10,000? We don't want it showing so often. Let's give that a go. 0.74, 0.01. As you can see, very quickly the error is reduced with the XOR gate logic. So that's good. Our logging is working. Great. That's all we really need to do for our neural network file, so let's head over to our other file. Now we have to think about how many inputs are there going to be in our system. I've always said that the goal was to turn our ship towards the closest asteroid and shoot it. So knowing that, we need to know the asteroid's position, don't we? So there's going to be an X position and a Y position, so that's 2 inputs. And we also need to know the ship's angle, because if we're facing this way, we need to know that we'll have to turn left to get to the asteroid, or turn right or whatever. So that's the asteroid X, the asteroid Y, and the ship's angle, so that'll be a minimum of 3 inputs. How about, just for testing purposes, we'll just turn the roid number down to 1. There'll be a single asteroid. Right, head down to where we set up our neural network, where we train the network. We don't need to do any of this XOR gate logic anymore. That was just for testing our system. And we don't need this test output anymore. So let's create some variables. We'll need the asteroid's X position, asteroid's Y position, the ship's angle, and just for completeness, let's include the ship's position as well. So ship X and ship Y. So the first thing we'd like to include in our training data is a random asteroid location. But we have to remember that asteroids can float off the left and right of screen, as well as top and bottom, up to their radius. So we'll have to include off-screen data here as well. So AX will equal a random point, random times by the width of the screen, so canvas.width. But because it can go up to its radius off the left and its radius off the right, well, that will mean we'll have to add the total with the size of the roid here. Roid size, which is the diameter in effect. Just bracket that. And then, so that'll generate a number between 0 and, just say the width is 500. So 500 plus 100 is 600, so 0 and 600. But we want it to be able to be negative, so we'll have to subtract the radius. So it'll be the roid size minus the roid size divided by 2, which is the radius. Do a similar thing for a y, except that it will be the height. Good. And now the ship's angle and position. Now the ship's angle, it'll just be random. We'll just randomly generate an angle anywhere between 0 and 360 degrees. So in radians, we'll just do a math random first. Math random times 360 degrees in radians, which is just pi times 2. Good. Now, the X location and the Y location, I'm not planning to move the ship at all. That'll be far too complicated. And I think it's a pretty good strategy just to sit in the middle, turn to the nearest asteroid and shoot. So we'll keep it fixed. So SX will just equal the ship's starting X, and SY will just equal the ship's starting Y. Next, we'll need to work out which direction to turn based on the angle of our ship and the angle of the asteroid. So, calculate the angle to the asteroid. How about we write a function for this, because it's possible that we'll use it again. Just down here, function, we'll give it a generic name such as angle to point. Angle to point, we'll have to use some trigonometry here. So we need to know our current position, so X and Y. We'll need to know our facing or bearing, we'll call that bearing. We'll need to know the targets, X and Y location, target X and target Y. And I think that's all we need to know. So let angle to target equal, well, it'll have to be the inverse tan because we have X and Y coordinates. So tan is opposite over adjacent. So A tan, there's two types of A-tans here. There's A-tan, which is our regular mathematics tangent, but that doesn't take into consideration coordinate space. You know how we have 4 quadrants in coordinate space? But A-tan 2 does take into consideration that, so we'll use that. Now it requires a Y and an X, so we'll have to find the differences between our target and our self. So we'll so this will be the Y differences. So it'll be target Y minus Y, right? And the x's will be a similar thing, target x minus x. However, because y's on screen, like pixel-wise, are in the opposite direction, so as we go up the screen, we're actually going in a negative y direction. So we'll have to apply a negative to that and a negative to that. So it'll be minus target y plus y, target x minus x. Y, x, yep, that's good. We'll have to find the differences between our angle to the target and our bearing. So we can just go let, say, diff equal our bearing minus the angle to target. Angle to target. Now that could result in a whole range of numbers, because this a tan2 function, it returns a number between effectively 180 degrees and minus 180 degrees, so it could be negative. Our bearing could be anywhere between 0 and 360, so just say it was 0 and we had 180 here, we'll get a negative number, won't we? If the bearing is, say, 360 and our angle is minus, we'll get a number over 360. So we'll need to do some normalizing as such here. So how about we have, well, we can just return this. I think return the diff. Remembering we can add 360 degrees to any angle and it's still the same effective angle. If I'm facing 40 degrees and I add 360 degrees, so 400 degrees, I'm still facing at the same angle, aren't I? So we will add 360 degrees, math pi times 2. But that could get us above 360, couldn't it? It'll get us above 0, which is what we want, but it could also get us way above 360. So we'll find the modulus of that, the remainder. So modulus math pi times 2. So that will guarantee us a result between 0 and 360 degrees, in effect, in radians, right? So back up here, we can just go let angle, say, angle equal, call that function, angle to point. We have to pass the correct parameters. So the x is our ship location, ship x, ship y. The bearing is the ship's angle. The target x is the asteroid x, and the target y is the asteroid y. So that'll give us our absolute angle as such. And then we need to determine the direction to turn, right? So that's probably, let's say let direction equal, well, if that angle is greater than 180 degrees, so angle is greater than math.pi, that's 180 degrees, then we'd like to turn left. So remember we have to put in 0 or 1 here. How about we set these as constants? I think that would be the best move. So back up here in our neural network parameters, let's have constant output left will equal 0. So that will be the expected output, expected neural output for turning left. Similarly, we'll have the output right, which will equal 1, and that'll be the expected neural output for turning right. Okay. So back down here, if the angle is greater than 180, math pi will output left, else will output right. So finally, we just need to train the network. So we can call NeuralNetwork.train to do that. It takes an input array. So the input array is just our position of our asteroid, AX and AY, and the angle of the ship. And the output array, the expected array, is just an array with direction in it. It's just a single length, sorry, a one length array. That's our training. So we'll be training that every iteration. Now, I foresee one problem where this AX, AY, and SA, they take on strange values. So AX could be a number like 600, AY could be minus 23, SA could be 3.8 or whatever, right? They're not normalized, are they? But let's see what they do. It might not be an issue. Okay, you can see that these errors don't seem to be getting any better. Let's pump up the number of samples. Just while we're here, that's the number of training samples. So we'll pump that up to 1 million. Let's see what that does. To me, that looks like it's not getting anywhere because these errors are still incredibly large. They're not getting any closer to 0. So I don't like that. So I think we'll need to normalize our data. We'll put that back to, we'll put that back to 100,000. I don't think we need 1 million samples, but 100,000 should do us. Head back down to our training here. We'll need to normalize this data here before we input it into the training array. So how about we create a method, a new function called, say, normalize input or similar. So just before shoot laser, function normalize input. We'll need to pass the roid's x location, the roid's y location, and our ship's angle. They're our 3 neural inputs. Now all we mean by normalize is normalize the values to between 0 and 1. So we'll divide them by something in order to get them to be between 0 and 1. So let's create a new array, an empty array called input. Let input equal empty array. And input 0, that will be our roid x value. We'll need to, now normally you could just go roid x divided by the canvas width. That would give us our screen position, our relative screen position. But because we've allowed it to be off screen up to its radius, then we'll need to modify this. So roid x, so that could be negative 50, could be negative, it could be the negative radius, it could be negative 50. So we'll have to add the radius back to that to get it back to 0. So roid size divided by 2. And we'll have to divide all of that by the new canvas width, including the radius on the left and right. So that'll be canvas width plus the diameter, which is just the roid size. Let's just work through that logically. So roid x could be minus 50. So minus 50 plus 50 equals 0. 0 divided by anything is going to be 0. That's fine. Now, the maximum value this could take would be, just say we'll choose an arbitrary width of 500. So 500 plus 50 is 550, plus 50 is 600. 600 divided by 500 plus 100 is 600, so that'll be 1. That's good. And halfway between, say 250. 250 plus the radius of 50 is 300. 300 divided by 500 plus 100 is 600. 300 divided by 600 equals 0.5. That sounds good. We'll do the similar sort of thing for the for the y position, except that we'll use the height instead. Now, the next one, ship's angle. This is a bit of an easier exercise. All we have to do is divide the past angle. So that'll be a number between 0 and 360, in effect, in radians. We just have to divide that by 360. So math pi times 2. So an angle of 0 divided by that would be 0. An angle of 360 divided by that would equal 1, and everything in between. That's great. Let's return that input array. So let's go up and implement that in our training section. Train the network. So all we have to do is normalize this data beforehand. Normalize input before we put it through our train function. Let's give that a go. It's looking better. At least it's getting closer to 0. There's some discrepancies here. Maybe we just need to modify some of the parameters here. So how about we bump up a number of hidden to say 20, and we'll set our number of samples to say 500,000. Just while we're here, we may as well change the amount of logging. Let's change that to say every 20,000 instead. Okay, let's give that a go. So it's a bit slower because we've got more hidden neurons, but it does look like it's getting better. The errors aren't too bad, are they? Look at that one down the bottom, very close to 0. So I think we've done quite well with that. If we put the hidden nodes back to 10, it'll speed it up a bit. Will that impact the quality? Let's have a look. That's pretty good too, actually. Either way, well, let's leave it at 20 and 500,000 number of training samples. Just while we're here, I'm thinking that we'll need an output threshold, because none of these predictions are going to be exactly 0 or exactly 1, are they? But they might be close. So how about we create a threshold, for example 0.25, just an arbitrary value to begin with. And this is how close the prediction must be. So how close the prediction must be to commit to a turn. So at 0.25, for example, if the prediction is 0.75 or greater, we would commit to a right turn. If the prediction was less than 0.25, we'd commit to a left turn. However, if the prediction was, say, 0.5, we won't do anything. We'll just sit in the middle. So how about we start implementing some of this? So let's go down to, well, first of all, let's see what happens when we push the left and right arrow keys. So in the key down method. So when we've got manual control of this, all we're doing is setting the ship's rotation to this. How about we create a function that can handle, because when we turn right, it's the same thing except we're going the opposite direction. So let's pull those out and create a function for that, because we'll need to call this function, what will we call it? Rotate ship. It'll just pass a boolean. We'll say that false equals left. Right, false equals left, and here we'll rotate ship. True, so it'll be right. And what do we do in the key up method? The key up just sets the ship's rotation to 0, so that's fine, we don't need to do anything with that. So let's go down and make that rotate ship just after our normalize input. Function rotate ship. It'll take a boolean, which is equal to right. So we'll be doing that. Now, if it's right, we want to put that as negative. So how about we make a variable called, say, let sign equal, now if it's right, the sign will be -1, else it will be +1, and we'll just multiply this by the sign. That should be okay. Just to make sure we haven't broken anything, how about we turn it back into manual mode? So automation on is false, and make sure that we can control this ship. Yep, I can turn left and right, no problem. That's all good. Put that back to true. And now let's go down to our update function. Where is that? Down here. To do, control the ship. So we'll need to make a prediction based on current data. So let's make some variables. So we need to know the asteroids x, which will equal roids. We'll just use, because there's only one asteroid to begin with, we'll just use roid 0 for the time being. Roid0.x. Similarly, ay will equal roids0.y. And we also need to know the ship's angle, don't we? So that's just the ship.a. Ship.a. Now to make a prediction, how would we go? Let predict equal, we just need to run our feed forward function. Feed forward. It will take the input array. So input array will be AX, but we have to normalize this, don't we? So hang on, do the normalize first. Normalize input. It takes the roids x, so AX, AY, and the ship's angle. Normalize input. Remember that returns a matrix, an output matrix, so we'll have to take its data, and there's only going to be one output, so it'll be the first column and the first row, first column, 0, 0. That should be our prediction. Now we need to decide which way to turn, so make turn. Now, we're going to get a value. It's not going to be exactly 0. It's not going to be exactly 1. So how about we find the difference between between the prediction and our left and right turns. So we'll call it delta left, or difference left, whatever you want to call it. Delta left will equal the prediction. Make this the absolute value, math absolute value. It'll be the prediction minus the output constant, output left. Right? And delta right will equal the prediction minus the output right. So let's just try to analyze that. So the prediction, just say the prediction is 0.2, right? So 0.2 minus output left is 0.2. That means it's 0.2 units close to the left. 0.2 minus 1 is 0.8. The absolute value will be 0.8. So that's not going to be what we want to do. So we'll have to compare it. We'll have to compare these to our thresholds. Okay. So if delta left is less than our output threshold, so if it's less than 0.25 or whatever value we choose to set it at, then we wish to rotate left. Rotate ship. Now left is just false. Okay, else if delta right is less than the output threshold, then we will rotate the ship right, which is true. Now, if it's neither, so for example 0.5 minus the output left is 0.5 minus output right. It's not going to be less than the threshold in either of these situations. So how about we just put an else here saying that so stop rotating. So if it's not confident, it'll stay still. So ship.rotate equals 0. So that's equivalent to us releasing the arrow keys. I think we should just log this prediction here. So console log predict, just so we can see if there's any problems with it. Okie dokie, let's try it. So we're just training it to begin with 500,000 samples. The errors look pretty good. That one wasn't very good. Okie dokie, what's it doing? It seems to be stuck. Oh no. No, it is turning. It's kind of slowly turning towards the asteroid. Will it turn when it goes past it? Yes. It's okay. It's maybe not the best. Now I wonder why. We'll just watch it a bit longer. It's kind of getting confused a bit, isn't it? Okay, I've been watching this for a while now. It looks like something's going wrong because it eventually, the ship, no matter how many times you run it, the ship eventually starts spinning around in a circle without, and it's got these really very confident predictions. So see this prediction here? It's very, very low. It's close to 0. So I'm guessing something's going wrong with our angle. So let's go into our code. Maybe we should log the angle here. Ship.angle. Let's see what that does. Okay, it's loading the training data again. Okay, so the angle, remember it'll be a number between 0 and 2 pi, which is about 6 or so. Now, that's not good. See the angle's going negative there? We want the angle to be 0, between 0 and 2 pi. So there's something, I think I might know what's wrong. If we head down to where we rotate our ship in the update function, I suspect that we're just letting it add on endlessly. We are. So for example, the ship angle can just keep going up and up and up and up. So it'll go beyond 720 and so on. It could go below 0, no problems, which is fine. It was working fine in the game. But for our prediction, we want it to be between 0 and 360. So we want to keep the angle between 0 and 360, which is 2 pi, remember? 2 pi. So if the ship's angle is less than 0, we'll need to add 360 to it. Remembering if we add 360 it'll still be the same angle. So plus equals math pi. Do we need to bracket this? I'm not sure. I'm not sure what the order of operations are for these assignment operators. We'll just bracket it, it won't hurt. Math times 2. So we'll add 360 to it. Else, if ship's angle is greater than or equal to 360, math times, I'll bracket this one as well, math dot pi times 2. If it's greater than that, then we'll want to subtract. We'll want to do the same thing except that we'll subtract 360. We don't want exactly 360 because our randomly generated position will never be 360, I don't think. Minus equals that, and that should do it. Let's give that a go. Let's load it up. Loading the training data. So the training data looks pretty good. It should be working quite well. Okay, I think that's acting a lot better. Where's the asteroid? There's the asteroid. Yeah, I think it's tracking it quite well. I think that was our problem. Yep, so it's choosing the first asteroid, which is whatever's in the array, first in the array, and following it. Good. Okay, how about we add some shooting to this little ship? So let's head back all the way up to the top to set some parameters. So we'll probably need to give the ship a rate of fire. So just under our neural network parameters here, let's create one called rate of fire. And we'll set that to say 5 shots per second. So shots per second. We'll also need to keep track of how many frames we count down to the next shot. So where we set up our neural network here, let's just put in a new, something called, say, AI shoot time. And we'll set that to 0 to begin with. Where will we update that? Well, we'll update that in our auto, where we do our prediction. So just after we make a turn, now what's the strategy for firing? When will we shoot? Well, we could shoot just when it's not rotating, but that's not really what I do. I keep turning and just shooting all the time because eventually you're going to get lucky too. So how about we just shoot all the time? It'll shoot as often as it can. So shoot the laser. If AI shoot time equals 0, which it'll start at 0, then we want to reset that AI shoot time, not this. AI shoot time will equal the frame rate divided by the rate of fire. I think we should find the ceiling of that. Math.ceil. So if we had a frame rate of 30 divided by the rate of fire of 5, that'll every 6 frames will shoot. If it was 10, so 30 divided by 10, we'd be shooting every 3rd frame, so quite quickly. We'll need to shoot the laser. Shoot laser. Just checking that function, because part of that condition is that the ship can shoot, and when we shoot a laser, the ship can't shoot. That's because the player must push the space key, then release it. So we'll have to set that up to be able to handle that. Or we can just do it here. Ship.canShoot equals true. So whenever it can fire, we'll let it fire. Else, so if the AI shoot time doesn't equal 0, we'll want to count down. AI shoot time minus minus. So this is just counting down the frames left. So let's give this a go. So loading in our training data. So hopefully this little ship will follow the first asteroid and just keep shooting at it until it's destroyed, and then it'll follow the next asteroid. Yeah, that's what it's doing. Bang, 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 bang. Yeah, just keep shooting. It's pretty effective, actually, even when we're not targeting the closest asteroid. So how about we program it to target the closest one? So head back into our update function. So compute the closest asteroid. We'll need to keep track of the index, so how about we just make a variable called, say, let C equal 0. So this will be the closest index in the array. We'll need to calculate the distance. We'll need to keep track of the closest distance. So we'll call that, say, distance 0 will equal, we have a method for calculating distance between points, the x1, y1, so the ship.x, the ship.y, the x2 will be the asteroid, so roids 0.x, roids 0.y, and then we'll have to loop through each of the asteroids. So for let I equal 0, actually let it equal 1 because we've already calculated the first one, distance 0 there. So let I equal 1. I is less than the asteroid's length, roids.length, I++. And then we need to get the distance of the current asteroid, so we'll call that distance 1. Distance 1 will equal distance, it's going to be the same thing really, basically, except that we'll be using I instead of 0 here. And then all we have to do is do a check to see if that distance is smaller, less than the current distance. So if distance 1 is less than distance 0, that means it's smaller, doesn't it? So we'll replace distance 0. Distance 0 will equal distance 1, and we'll want to update our index, closest index. So C will equal I. So all we have to do is put that C into where we've got 0 down here. So AX will equal roids C, AY will equal roids C.Y, and let's give that a go. Loading our training data again. So hopefully it'll turn towards the closest asteroid and shoot at it. There's only one asteroid here. That reminds me, we should probably up the number of starting asteroids back to its original. So roid num will equal 3. Save that. Load it one more time. Okay, is it turning towards the closest one? Certainly it's not shooting the furthest away ones anyway. So it's doing fairly well. It's not perfect. I'm thinking we could probably make this a little bit better. I think we'll do one more update to our little function here. How about we pass some more information, because we're only passing kind of the bare minimum. We're passing the asteroid location and the ship's angle. I think we can do better than that. So head back into the code. To head down to where we set up our training data. What else could we pass? Well, we are calculating the angle to the asteroid. How about we stick that in as one of our inputs? So we'll put it in after our asteroid position. We'll have to bump up the number of inputs to 4. So down here, our normalize input, we'll have to add an extra here. We'll call that roid angle. Roid angle, it'll be our third one. It's going to be very similar to how we do the ship angle. We'll just put roid angle there. Roid angle. Ship angle will update its index to 3. Wherever we call this, we'll have to fix it up, which is just down in our update function. So we'll have to pass an angle in there. And we'll have to calculate that angle. So what do we need to know for that? We need to know the ship's x and y coordinates. So Sx will equal ship.x. You don't really have to do this, but this is just to make it clear. Ship's y, ship.y. And let angle equal angle to point. Now what does it take? X and y, which is the ship x and the ship y. It takes the bearing, which is the ship's angle, the target x, which is the asteroid's x, and the asteroid's y. And then we'll pass that in through our feed forward function to get a prediction. I don't think we need to log this anymore, this prediction. Let's take a look at that. Okay, import, doing our training. Wow, those errors are very small. See they're e to the minus 15? There's a couple of zeros in there, so they're very precise. So looking at our ship's performance, yeah, he's doing pretty well. He should be doing very well. The only issue I can see is that, see that jitter there? That's because we're only making a prediction every frame. If we increased our frame rate, we could probably make that better. And also if we reduced our threshold to decide whether we turn or not. So let's do that now. So head up to the top. We'll reduce our output threshold to say 0.05. That means in order to make a right turn, we'd have to have 0.95 confidence. Let's increase the rate of fire for fun, just say to 15 shots per second. And we want to increase our frame rate to say 60. Let's give that a go, eh? Okay, just loading our training data. The errors are very, very good. And here he goes. Wow. We've created a monster. So with his increased rate of fire and the faster frame rate, he can make more accurate, more subtle turns and really pepper those asteroids with laser fire. Cool. So anyway, that's the end of our tutorial series. So we've gone from using matrix maths to creating a neural network, only a fairly simple neural network, but a neural network all the same. I hope you've learnt a lot from this. I certainly have, because I had to do a lot of research in figuring all this stuff out. But in the end, we managed to use our network to control a simple game, such as asteroids, and this is the result. So I wonder how far he could go. How far could this, what level could this ship reach? Well, anyway, feel free to download the code and try it out for yourself, update the parameters, have a play, and learn something new. Until next time, talk to you then. Bye!